Okay, so let's get started. Okay, so this week is your demo for your first lab, correct? I mean your lab 2, okay, which is on the analog sensors. Okay, so as mentioned, this Wednesday you must do the demo. So during the demo, the lab TA will ask some questions, okay, to gauge your understanding and how well you have understood the code and the hardware that you have built. Okay, that will be some marks the demo plus the report. Okay, so I've already created a submission folder in IVLE. Okay, rightfully the submission folder is supposed to be this Friday. Okay, but since this is a holiday weekend, I have put the submission for next Wednesday. Okay, so the submission due date is next Wednesday. Okay, so if this weekend you win money during Mahjong, please remember me. Okay, if you lose money, then you remember your friend. Okay, Ken? So submission for your IVLE, your report is due next Wednesday only. Okay, so you don't need to rush over the weekend. Okay, it's due next Wednesday. Okay. Ken, any questions? So this Wednesday is still, you have to do the demo. You have to do the demo. The report will be due next Wednesday. Okay, so let's come back to where we started, where we stopped the last lecture. Okay, so last lecture we were talking about the threads and the different states of the thread. Okay, so again this is important, okay, because you must understand the concept that at any point of time you have a lot of threads in your system. Okay, a lot of threads in your system, and only one thread will be running. Okay, and the rest will be in a different state. What state they are in depends on the situation. That means they could be in a ready state. Okay, they could be in a block state. Okay, so they can be potentially in a lot of different states. So after I create, okay, after I do the creation, okay, by default, let's say I had 4 tasks, task 1, task 2, task 3, task 4. When I create the 4 tasks, all my tasks by default will go to a ready state. Okay, but at any point of time, only one of the tasks will run. Okay, generally, when you talk about OS-based system, the task that is selected to run will most probably be the one with the highest priority. Okay, so each of these tasks here, okay, will have a priority. Okay, so the task that has the highest priority will be selected to run, and while that task is running, so assuming that maybe task 3 has the highest priority, so from ready it switched to run state. Okay, so when that happens, the other tasks would still be in a ready state. So when task 3 is running, okay, the other tasks that are in the ready state need to wait for their turn. Okay, so how will they get their turn? They will only get their turn when task 3, which is currently running, is forced to give up the CPU. How will the task 3 that is currently running give up the CPU? So there's a few ways. One is when it's running, you can go back to ready state. Okay? How can you go back to ready state when it's running? You may call the yield function. Yield function means I voluntarily give up the CPU. Okay? So if I voluntarily give up the CPU, then I allow other tasks to run. Okay? Or I can be preempted. But if I'm preempted means what? That means another higher priority task is now going to take over the CPU. Okay? So maybe there's another new task that was created along the way called task 5. And that is a higher priority than task 3. Okay, so if there's a higher priority task that suddenly is ready, then the current task can be preempted. Okay, and this new task can run. Another scenario is the task 3 that is currently running is trying to acquire a resource. Okay, so this term resource, okay, you will see quite frequently being used And what does this refer to? This resource could be a memory, it could be a hardware block, okay, it could be some data that is waiting for it for arrival on some of the port. So it could be anything. Okay, the resource, when we say resource, is a general term. So when we say a task is waiting for a resource, okay, it could be that it's waiting for somebody to press a button, or it could be waiting for somebody to send a message over. Okay, so this resource could have been a message, it could be a memory, okay, it could be data. Okay, so it's a general term. So when we say a task waiting for a resource, that resource is not available. Okay, if a resource that is waiting for is not available, then from running state, it will go to a block state. Okay, so there's a difference between block and ready. When you say ready means, I have everything, but maybe somebody else, higher priority is taking over. But when I say I am blocked means, I currently am missing something. That means I need some information, some resource, but I'm missing it. So I go to a block state. When I go to a block state, okay, because I'm missing a resource, I need to wait until somebody give me the resource. Okay, so only when that resource is available to me, then from the block state, I'm able to go back to a ready state. Okay, and then again, from the ready state, when it's my time to run, I will be scheduled to run. Okay, so this is the general flow of tasks. Okay, when I say I'm terminating a task, basically means that's the end. That means I maybe created a task for a specific purpose, one-time event, and after that, I know that event will never happen. Okay? So what will I do? After I create the task, it do what it's supposed to do, then I will just go and terminate it. I know I don't need to do it anymore. Okay? What type of task could be a one-time task? If I create a system, which type of task will be a one-time task? I do one time, you don't need to do. Like what? When you first buy something, correct? When you first buy a handphone, correct? When you switch it on for the first time, that first task that you run is the setup task, correct? He'll ask you go and calibrate your finger, go and set your clock, set your time, correct? But after I do all that, I don't need to run anymore already. Correct? So usually those setup tasks, initialization tasks are those tasks that only need to run the very first time when the system power up. Okay, subsequently, you do not need to run it. Okay, so that is your process state, okay, and we covered this in terms of the aspect of how it comes into play. Okay, so again, from running to go to ready. When I'm in the running state, for me to go to the ready state, what are the possibilities? Okay, I call a yield. Okay? Okay, so if I call a yield means I intentionally give it up. Okay? Or from running, I can also go to ready if there is a preemption. Okay, so from running to ready, okay, these are the two possible scenarios, either yield or preemption. Running to block. Okay, running to block means is in the case where I want a resource, okay, and that resource is not available. Terminated, okay, again, we will usually not do it unless it is a specific case where it's a one-time task. In most of our programs that we do, we don't necessarily terminate tasks. We create a task for a continuous reason. Okay, so now that I know that my task can be switching from ready to run to block and so on, it means that any point of time, my CPU must be able to handle this switching. Okay, if I'm running one process and suddenly another higher priority task wants to take over, so I must be able to handle this switching. Okay, And that switching is basically what we call the context switch. Okay, that switching is what we call the context switch. Okay, and basically what happens in context switch, if I'm currently executing process 0, P0, okay, and I'm in executing state, and at this point of time, okay, P1, okay, P1 wants to take over. So if P1, which is a higher priority task, wants to take over, then the scheduler must come in to do this context switch for me. Okay, so what is context switch? Context switch means the current process P0 must be able to suspend, and the new process P1 must be able to take over. So during this context switch, what must happen? So when the operating system will come in to save the state, the current state onto PCB0. PCB is what? The process control block. Okay, a process control block is what? Okay, so if you look back here, the process control block is basically a block of memory that will hold all the information related to a particular process. Okay, so when I create a process, okay, it will contain all this information: your program counter, your registers, your memory, your state, and so on. So all the information related to a particular process. Okay, so if I have a process to read an MP3 file, okay, so when that process is running and suddenly it gets preempted, I must be able to know exactly what I was doing, which file I was accessing, how much memory I have consumed, okay, where is my pointer, and so on. So all of that is inside the process control block. So in the event that another higher priority task P1 suddenly wants to take over, and I'm forced to suspend this current task P0, I must be able to save the entire state onto the process control block of the current task. Okay? And then what must I do? I must be able to reload the state from process control block 1. Okay, why do I say reload? Because my process control block, or my P1, this process 1, could have also been executing before that, correct? It's not that a task run one time, run until completion and finish. No. A task that is started may never finish, because by the time it finishes, it's preempted, it gets blocked, okay, another task take over. So at any point of time, while I'm executing, okay, it doesn't mean I run to completion. I'm running, then halfway along the way, somebody else take over. So you're always going through this process of saving and restoring and switching between the tasks. So that's why I say reload. Okay, why? Because maybe before this, somewhere along the way, P1 was also executing. Okay, and then it was maybe forced to give up. Okay, and somebody else was running. So now P1 got a chance to run again. So since it got a chance to run again, I must reload the state from process control block 1. So when I say reload, what am I going to do? Now I'm going to go to the process control block of P1 and go and figure out, okay, what was it doing, where was the program counter, what were all the memory, registers and data, everything associated with this process 1, and reload it back so that I can now carry on from where I left off. Okay, so when I do a reload, I'm basically trying to do a context switch and be able to carry on from exactly where I left off. Okay, so when I do a reload, then I can now start to execute, okay, my new process. Okay, and while I'm executing process 1, again, something else may happen and I may trigger another context switch. Okay, so when I trigger another context switch, what must I do? I must save everything that process 1 was doing onto its own process control block. Okay, and then reload the state of the new task I'm running. Of course, in this case, I'm saying PCB from process 0, but it could always be a new process, process 2, correct? It's not only 2 tasks, I can have a lot of tasks. Okay, so at this point of time, when I am forced to give up P1, I could be actually jumping to a new process called process 2. And process 2 may be running. taking over the CPU. Okay, or I could also be jumping back to process 0 here. Okay, this decision, okay, is not something that you worry about. You only are concerned about creating the thread and setting the priority and making sure that if I am preempted, if I am unable to complete my task, I am still able to hold on to the data correctly. Nobody is going to come in and corrupt my data, corrupt my information. Okay, so when you write your task, you must put in necessary safeguards. Okay, because you can never guarantee that you will run from start to the end. It will never happen. You will start, but along the way, many times you will be preempted. Okay, you will be forced to give up. So you must always make sure that whenever I am preempted, when I come back, I am able to carry on from where I left off. Okay, so this context switching time is again part of our overhead. Okay, because this is the time that you take to switch between one task to another task. Okay, so of course during this time you are not actually executing any program, but you are making use of the CPU to do this switching between one process to another process. Okay, so what usually happens? Okay, what usually happens in your design? So when you are creating your project, okay, with a multitasking system, what will you do? You will see that your code base comprises of interrupts, okay, for your ISRs, plus you have tasks. Okay, take for example this. Okay, this button here, okay, is to maybe trigger a camera. Okay, to trigger a camera. So when the user presses a button, I activate the ISR. Okay, so the ISR is activated to let me know that somebody pressed the camera button. But when the camera button is pressed, then I must activate the task to go and take the picture, correct? Okay, so this interrupt service routine must send a message to this task to go and take a picture. Before that, you will see that the task is blocked. You do not want your camera to be continuously taking pictures throughout the day, correct? Okay, but your camera functionality must be there on standby mode. It's a block state. It's waiting for the event that somebody go and press this camera button. So when I press this camera button, okay, so if you look at the code flow, how will it be like? The camera button trigger the interrupt service routine. Okay, the camera button trigger the interrupt service routine. This interrupt service routine will send a message. Okay, so it means what? That means this task 1 was blocked because I'm waiting for a resource. In this case, the resource is what? The message. Correct? That means task 1 is blocked because it is waiting, okay, for, okay, it's waiting for a message. Okay, it's not waiting for anything else. It's waiting for somebody to send a message. Okay? So who will send the message? The interrupt service routine will send a message. When will the interrupt service routine send a message? Somebody trigger the interrupt with the button. Correct? Okay, so when the user press a button, it triggers the interrupt service routine. Interrupt service routine will now send a message to the task. So the task, what will it do? From the block state. So from the block state, okay, it will now go to the ready/running state. Okay, so why do I say ready/running? Why cannot say from block state go to running state? Because I already received the message, right? Okay, that a camera has been activated. So why can't I straight away go to running? Because, okay, there is no way to go from block to running. There's no such way. Okay, your task can never go from block to running. Your task can only go from block to ready. Ready to running is always decided by your scheduler. Okay, you cannot decide when to run. Your scheduler must decide who should run. Okay, so that is why sometimes something important happen, you press the camera button, you want to take, bloody hell, the screen don't want to come up. Correct? You waiting, you only see the black screen. You cannot take picture. Okay, why something else happen? Correct? Some other higher priority task happen, or your task get blocked. Something happened that blocked, okay, that prevented your task from going from ready to running state. Okay? So, you can only say from block, I go to ready. From ready to running, your OS must handle it. Okay, so even though I have an ISR, the ISR send me the message, all I can do is say, okay, go to ready. And hopefully nothing else mess up, and I am able to go from ready state to running state, and my camera can immediately activate for me to take a picture. Okay, so after I take a picture, what must I do? I must be able to do some image compression, I must be able to save it, correct? Okay? Again, that image compression, that saving, that file system may be a separate task. Correct? This task 1 may only be there for me to take the picture. After I take the picture, I get the raw data, I may have another task to do the compression, another task to do the file system and go and save it in the correct folder and so on. So what must I do? After I take the picture, I get the raw data, I may send a message to another task, correct? Okay? So what will I do? After I take the picture, this raw data I can put inside some buffer, correct? Okay? The raw data that I take from the camera module, I put it into a buffer, and then I send a message, okay, to task 3. And maybe task 3 is supposed to do the compression and file saving. So when I send a message to task 3, what will it do? Again, task 3 is blocked all the while, correct? Because task 3 is blocked because it is waiting for, again, message, okay, from task 1. Okay, it's waiting for a message from task 1. So only when task 1 send me a message, okay, then I wake up. And task 1 will only send me a message after it captures the raw data and put it in some buffer. So task 3 knows that, okay, once I receive a message, means somebody has already taken a picture and put the raw data into a buffer. Now my job is to go and do the second part, okay, which is maybe the compression and saving onto the file system. Okay, so this is the general idea when you break up your whole objective into multiple tasks. Okay, so this is how you must also think when you're creating a project that is running on OS. Okay, in the past you will say sequential, correct? Okay, button press, go and activate camera module. After camera module takes a picture, I go and save it, I compress it, then I save it, then I go look back again. Correct? That is your single-threaded thinking. Now in a multi-threaded, you must think of all the different functions that I need to fulfill. How many tasks do I need, and how will they communicate? Okay? So each task has an objective, but at the same time, there is a way for me to synchronize. So I can say that task 3 will only run after task 1 has completed a certain part of the activity. Then I trigger task 3. Okay? So when task 3 is running, okay, task 1 may go back to a ready state or a block state. Now waiting for the next trigger to happen. Okay, so this is the general flow of code, okay, and processing within an embedded system. Okay, so this scheduler is again a very, very important part of the system. Why? Because the scheduler is responsible for making the decision for you. Okay, the scheduler is responsible for making the decision for you on who will be executing. Okay, so at any point of time, you have a lot of processes, a lot of tasks in the system. Your scheduler will be responsible for who should execute, okay, and when I should do the switching. Okay, so when a task is created, you only can put it in ready state. Your scheduler is responsible for deciding whether the task that is currently in ready state should go to a running state. Okay, so let's come to the concept of the threads. Okay, so in the past now we were talking about the process and so on. So what is thread? Okay, so threads and process, again, very, very similar. You will see that we use them interchangeably. Okay, but it's just that we generally refer to process at a higher level and threads at a next level. So when we talk about a process, we say we have a single flow. Okay, and we talk about a multi-threading, we say we have multiple flows, okay, within a process. Okay, what does that mean? So we need a process, okay, within a process 1, for example, I can have multiple threads. A process 2 may have multiple threads and so on. Okay, so example, now I have a media player. Okay, and this media player is your process 1 here. Okay, so for a media player to function, what must it have? It must be able to have user interface. It must be able to do decoding. Okay, it may also do live streaming from the network, or it may also be able to retrieve data from your file system. Okay, so your process 1, which is your media player, itself has multiple threads. Okay, process 2 may be what? Process 2 may be another process that is also related to media playing. Alright? Okay, just like in your handphone, you may have different applications that fulfill the same objective. Correct? Okay, so you can see that in this process 2, you may also have a shared thread 1 and a shared thread 2. Okay, so thread 1 and thread 2 could be similar, could be different. Okay, so that is the good part of multi-threading. When you create a thread, okay, to do a specific task, it is not tied to a specific process. You can share that thread with other processes, correct? Because a lot of processes may need the same functionality. Okay, so to have a user interface, to be able to do decoding and playing of audio, okay, is not confined to a single process. Multiple processes may require the same ability. So I write the code one time, I have the functionality one time, but I can use it across multiple processes. Okay, so that is the advantage of breaking up the system into a lot of different threads. Same concept as function call. The main reason why we have function call, okay, when you write your C program is what? You only write it once, and then I keep calling it whenever I want to use it. Same idea with threads. Okay, when I create a thread with a specific objective in mind, I can share that particular thread code base with multiple processes, which also require a similar or a shared goal. Okay, so that is the whole idea of multi-threading. So when I say I create a thread, okay, it has certain components, again very, very similar to your process control block. Okay, very similar to the process control block. It also has its own code section, it has its own data section, it has a thread ID, it has a program counter, and so on. Okay, so you can see that a process and a thread actually are very, very similar. Very similar, except that a process, we usually refer it to a higher level application, and the thread refers to the lower level task that you want to fulfill. Okay, so again, always come back to this idea. Imagine that a process is a media player application, and the thread is all the individual tasks that I need to be able to fulfill in order for the media player to work. Okay, so again, the same idea is here. Okay, when I say I have a multi-thread, okay, that means I'm able to break up my system into multiple threads that will run concurrently, but at the same time, there is also inter-process communication. Okay, like how just now we saw, a button may trigger one task, that task may send a message to another task, and so on. Okay, so that is the idea behind single thread and multi-thread process. Okay, so this again, no need to worry too much, they just give you an idea. When we look at the example, you will see. Okay, so let's look at the case study, which is your free RTOs. Okay, free RTOs is basically the RTOs that we are using, okay, for your project. Okay, so when you say free means what? Okay, everybody likes free, alright? And the moment we say free, only everybody queue up. Okay, so when we say free, basically means, okay, you don't need to worry about any licensing fee, okay, to use it for any commercial product out there. Okay, you use it, you develop it, you sell it in your product, doesn't matter, it's free. So it also means what? Okay, so the few things you must remember when it's free, your support is who? Who will support you? The whole world, because everybody wants free stuff, correct? Okay, so the whole world supports you. So you got any problem, what do? You go to Google, and hopefully Google will solve your problem. Okay, so that is the thing you must remember. Okay, so of course it also means that you don't need to worry about any upfront fee, you don't need to worry about any licensing fee. As long as it works, okay, you are happy. Okay, so why is free RTOS popular? Because it is free and it has been widely used for a lot of embedded applications. Okay. There are also a lot of other RTOS that is available, that is paid version. Okay, some of it they also give you free, but with some limitation, correct? Okay, that means, and in most cases the limitation is what? Your code size. Okay, they say, okay, you can use the full-fledged OS, but you are only limited to compile a code within maybe 32 kilobyte or something. Okay, so that is the some of the limitation. Okay, so some of the more commercial RTOS out there that companies use are things like maybe ThreadX, okay, Micro COS, and so on. Okay, so there are a lot of other RTOS that is available that organizations use, and they prefer to use the paid version. Okay, why? Because at least if there are issues, there is somebody to support them. Okay. Okay, so let's look at free RTOS, which is what you're going to be using for your this module in your project and in the later labs as well. Okay, so one thing, it is small footprint. Okay, when you say small footprint means what? Your OS itself occupies memory, correct? And your OS is basically a system, a code base that is running to manage all your threads that you're going to create. So for your OS to execute, it's actually going to consume some amount of memory. Okay, just like when you buy a Windows PC, correct? When they say you have 128 gigabyte of your SSD, is it all that you have that you can use? No, correct? Why? Because a portion of it, okay, already used by your Windows, correct? Okay? When they say I sell you this PC 128 gigabyte SSD, doesn't mean your 128 is fully available for you for storage. Okay? A portion of it may already be used by your OS. Okay, so maybe 8 gigabyte already used. Okay, just give you a number. So maybe 120 gigabyte is available for you. Okay, to use for your storage. Same thing when they sell you the RAM. Okay, so if I say I got 512 megabyte RAM in my PC, also doesn't mean you have 512 available, because when your Windows loads, already it occupies some memory, correct? Okay, so maybe from 512 it already occupies 12 megabyte. So you only have 500 megabyte left to use. Okay, so for your PC-based system, memory is extensive. Okay, from 512 megabyte, you go down to 500 megabyte, you don't really feel it. Okay, but for an embedded system, memory is very expensive. Okay, whether is it your RAM space or your ROM space. So you want to make sure you use as small amount of memory as you can for your OS. You do not want a OS that consumes 50% of your memory. Then you can only have the remaining 50% for your actual application code. Okay, does that make sense? Okay, so you want to minimize the footprint as much as you can. Okay, open source, again, because it's free, so your whole world is your community. Okay, portability. When you say highly portable, means what? This highly portable doesn't mean what? You carry along in a thumb drive. No, it's not that portable. This portable means what? When you say it's portable, that means you are able to map it to different CPUs. Okay, or in other words, different microcontroller. Okay, in this particular lab and this module, you are mapping it to your Arduino Uno, which is actually what? Your Atmega 328P microcontroller, correct? Okay, but in future you may be doing a project on a different microcontroller, maybe ARM microcontroller, or Intel microcontroller, or Motorola microcontroller. Okay, so when I switch to a different microcontroller, I may also want to use the same OS, correct? So since it is a very highly portable, it may be easy for you to find references on how to map or port this OS over to a different microcontroller. Okay, so I can still use very much the same code base when I switch to a different microcontroller later on. Okay, so that is what you mean by highly portable. Okay, and real time, again, the main idea of real time is for you to be able to create all your tasks and for all your tasks to run concurrently. Okay, so in FreeRTOS, basically you create a single process and then you create multiple tasks within a single process. Okay, so that is the whole idea of FreeRTOS. Okay, it shares the same address space with your tasks, and one of the key things is just a simple library. Okay, sometimes to port an OS to a microcontroller can be a real painful experience. Okay, when I say painful, why? Because you may have to do a lot of configuration, change a lot of files, okay, and do a lot of setting before you actually can incorporate your RTOS into your system. Okay, when I say RTOS in your system means what? The development environment you're using. Okay, in this case, you're using the ML Studio, alright, for your code. So in order for me, or in order for you to be able to write your code on FreeRTOS and compile it within your ML Studio 7, you may need to do a lot of settings. Okay, a lot of configuration. But luckily for us, FreeRTOS is just a library. Okay, so all you need to do is to incorporate it as a library. Okay, and then you can straight away use all the functions that FreeRTOS provides. Okay, so it's actually very, very easy to include FreeRTOS into your project. Okay, just include it as a library and everything is there. Okay, so that is the general idea. Again, you will actually do it in the lab, so you get a feel of how it is. So these are the FreeRTOS start state. So you can see that they are very much similar to what we saw just now. Just now what we saw is the general idea. Okay, now we are looking at FreeRTOS in particular. Okay, so this comes back to understanding that different RTOS may have slightly different terminology. Okay, the way they call the names and so on. So we must be familiar with how each RTOS calls it in terms of the naming convention. So this dot means what? That means the starting point, correct? Okay, the starting point. That means before I do anything, when I create a task, it first goes into a ready state. Okay? When I'm in a ready state, I may go into running, and from running, I may go back to ready. Okay? If I want to suspend the task, okay? When I say suspend the task means I may intentionally want to put my task on a suspended state for a period of time. Then I call this function. So if I call this function, I will go to a suspended state. From my suspended state, if I call this vtask resume, I come back to a ready state. Okay? If I'm running and suddenly I realize that I don't have any resources that I need, I may go to a block state. Okay? And from a block state, again, I may go back to a ready state if the appropriate resource becomes available. Okay? Again, you will see that from ready to running and from running to ready, there is no call. Again, why? Because you do not decide. Who decides? Your scheduler decides, correct? That's why from ready to running and running to ready, the arrow is there, but there is no call because you cannot decide. The scheduler will decide for you. Okay? But if I'm running, I can also always call suspend. Then I can go to a suspended state. So this is, again, how your task will play around inside the free RTOs. Okay, so before we go into your free RTOs actual code, okay, let's have a quick quiz and then we will go for a break. Okay, so stand by your phones and then we'll have this quiz to review this concept and then we'll go for a break. Okay, so please connect with the code. So again, there's a healthy gourmet protein bar for the winner. Protein bar, just because you protein bar, you cannot get must win. Anybody else? There's still a few who haven't signed in. Okay, so let's get started. So total 5 questions. Okay, so round robin architecture means what? Round robin means each task takes its turn to run, correct? But it doesn't mean that each task will take the same amount of time, correct? Each task may be doing different things. One task may be checking switch, one task may be checking activating LED, one task may be sending data and so on. But it's just the concept is every task will do something from task 1 to task n and then I loop back. Okay, but I do not know whether each task will take how much time. Okay, so the answer is false. Okay, so again, a round robin, Though it is an easy way to break up your whole program into small program, the problem is what? Because each task may take different amount of time. When I'm doing one task, the other tasks all will have to wait. And if the other tasks are waiting and they are supposed to capture some input, I may miss it if a task takes too long time. Okay, next. Okay, one is in front. This one should be easy. Half the class. ISR should be as short as possible. Okay, ISR should be as short as possible to do only the minimum and most critical amount of work. The rest of the data processing should be done by application routine. Correct? That's the whole idea of ISR. Don't make your ISR long, because if your ISR is long, then it defeats the whole purpose of ISR. Okay, the whole purpose of ISR is some event happen that is important. When it's triggered, I go in to go and capture the data, capture the event, and do what is really important. Okay, subsequently, I should allow my application routine to finish up. Okay, so that is the whole idea. Okay, process with all the required resources can still switch from running to ready state. Think carefully, think carefully. I know you all like to fastest finger first. Okay, so when I say I have all the required resources and I'm running, I can still go to ready. Why? Because somebody else that is higher priority can preempt me, correct? Okay, if I have all the required resources and I'm running, I may still be forced to give up the CPU if a higher priority task is going to take over. Okay, so that's the whole idea of OS. Okay, though I'm running, somebody more important can take over the CPU. Okay, so that's why it is true. Somebody else, you can still take over if they are classified as higher priority. Okay. A thread that is currently in a running state will go to a block state because okay, so when I'm running, I will only go to a block state if a required resource is not available. Okay? If I am running and I have all the resources and I get preempted, that is not block, that is called ready state. Okay? So you must always be very mindful of the terminology we use when we classify your state. Okay, when I'm running, I will go to a block state when a resource that I want is suddenly not available. Again, this resource is a general term. It could be a message, it could be data, it could be a memory, it could be anything. Okay, when I want it and it's not available, then I cannot carry on, so I become blocked. Okay, until the resource becomes available. Okay, last question. Okay, a task that is ready will definitely get a chance to run. No, we cannot guarantee that every task will get a chance to run. Why? Because if you write your task in a way that it never give up the CPU, correct? Then there is a chance that your other task will never ever get a chance to run. So the way you write your task is very important. If you write a task in a way that is an endless loop and you never have an opportunity to give up the CPU, then your other tasks may never get a chance to run. Okay, so we cannot guarantee that a task just because you create it is there in the system, it will run. No. It still depends on how you code it. How you code all your tasks will determine whether all your tasks get a chance to run. Okay, so this is important, because when you write your project, when you develop your project, okay, you say, hey, I already created my task, but then it's not running. Okay, why? Because maybe the way you have written your other tasks never created an opportunity for this task to run. Okay, so the way you set your priorities, the way you decide when I go into a block state, when I go to a run state, all of this will play a part. Okay, so the winner, low 5545, who are you? Okay, please come forward to claim your prize. The rest of you, all of us, will go for a 10 minutes break. Okay, he already got his break. The rest of you must go canteen. Okay, so 10 minutes break, then we will resume. Okay, so let's carry on. Okay, so let's look a bit more on how this task creation happens. Okay, so this task creation, when you create, you're supposed to use this API call. Again, like I said, when you compile this free RTOs, you compile it as a library that will be included in the project. So you're just going to call the functions related with the free RTOs. Again, it looks scary, but don't worry. When you look at the example, you realize that actually it's very straightforward. Because when you look at the example, you know what is important, what is not important, and some of it is usually null or zero only. Okay, so these are the parameters that you need to provide. Okay, so the first one is a pointer to the function. Okay, pointer to the function to represent the entry of the new task. Okay, the second one is the name. Okay, the name that you're giving to the task. Okay, next is the how much stack space you need. Okay, the stack space is basically dependent on how much memory you think this particular task is going to consume. Okay, this is to pass parameters. Sometimes when I create a task, I already want to pass parameters. Okay, in most cases, you will usually pass parameters through a message or a queue or so on, but occasionally you may also want to pass parameters when you create a task itself. Okay. Okay, this one is important, the priority. Okay, so again, this priority is very important in deciding who the scheduler will pick to run. Okay, and then finally the pointer to the task handle that can be used in the future. Okay, and then the return status. Okay, so when I create a task, okay, the RTOS library is supposed to give me a return function or return parameter to know whether is it successful or unsuccessful. Okay, this shows you a simple example. Okay, like I said, when I look back at the numbers, I look back at this example and look back at this now, you will see that actually it's not so, nothing much to worry about. Okay, so if I look at it, basically what I need to do, you can see that this task 1 is the name given here, correct? The name of your actual task. Okay, the name of your actual task. This is a name that you give it, and again, you can give any name you like. Why do you have two different sort of labels? Okay, one, this label is referring to the actual function inside your code. This is actually used when? This is generally used when you're debugging the code. Okay, so if your development tool allows you to do debugging, okay, that means you can put breakpoint, you can do JTAG debugging and so on. That in the debugger mode, they will usually refer to this particular name. Okay, this again is the number, how big is your stack. Okay, in most cases, you will use the default number. Okay, we'll just stick with 256. Okay, and then we say null to null. The last three parameters again are what? These parameters and the pointer to the created task. So we don't need these two, so we just say it is null, null and null over here, and this 2 is the priority. Okay, so we give this a priority 2. Okay, so later we will come to more on the priority and so on. Okay, so let's look at this task here. Okay, so in this case, what does this example do? You are creating a task, okay, called task 1, and what is task 1 supposed to do? Task 1 is supposed to do a digital write. That means it's supposed to do a on and off of the LED one time. Okay, and that's it, correct? Okay, so you can see that task 1 only does a few lines of code and that's it. Okay, rightfully, okay, when I hit this line, when I finish this delay and I come here, effectively your task 1 is not doing anything anymore, so it sort of ends over here. It sort of ends over there. Okay, so your task, okay, is not a function call. Always remember, when you create a task, when you jump to the task, you are not jumping to a function call. When you jump to a function call, what do? Okay, when I call a function, I jump to the function call. Okay, let's say this is my main program here, and I call, okay, function A. So I jump to my code called function A, I do, and then I return back. Alright? But task is not a function call. A task is created to run as if it is owning the whole CPU to itself. Okay? So if I create a task that is only going to do these 4 lines, you will do these 4 lines and that's it, that's the end. There's no returning back. Okay? So rightfully, this is not the correct way to write a task. We're just giving you step by step, but this is not the correct way to do things. Okay? Of course, in this scenario, what happened? Your task 1 is created, it runs, it executes this 4 line code, and that's it, it disappears. Okay? So rightfully, what must you do? Okay? Since you no longer want to do it, okay, you want to free up the memory that your task originally consumed. Okay, and how do you free up? You can delete yourself. Okay? Even if I don't put this line, your task 1 will only execute 1 time. But what's the difference? The difference is what? The difference is if I call this S task delete, I am going to delete this task. That means I'm going to delete the memory that was allocated when I created a task. Okay, so I free up the memory for other things. Okay, I free up the memory for other things. Okay, so in this case, this is an example of a one-time task. Okay, I create the task, I execute 1 time, and after I execute 1 time, I delete myself. That's it. Okay, so this is an example of a one-time task. Okay, but rightfully, you do not want to do that. Okay, another difference between just now is now you add this task handler here. Okay, and what is this task handler? Task handler is, if you look, is the pointer to the task handler to be used in future for reference to the task control block. Because after I create the task, you have to remember that I have created a task control block, correct? It contains all the parameters related to my task. How do I get reference back to this task control block? Is through this task handler here. Okay, so you can see that this second code here adds 2 things. One thing is the task handler. So I must first create a task handler variable parameter and call it using the address here. And I do a task delete function here to delete the task after I finish it. Okay? But in most cases, your task is written as an endless loop. Okay? Rightfully, when you do your project, when I do a task, okay, when I do a task, okay, when I do a task here, task 1, my entire code is actually inside a while 1 loop. Okay, that means this particular code here must be inside a while 1 loop. Because your task must be created to run forever. Okay, so of course now it leads us to the next question. Correct? If my task is written in a while 1 loop and it's going to run forever, then how will my other task get a chance to run? Correct? If my one task already is going to run in an infinite loop, how will my other task get a chance to run? Okay, so that is where you need to put in certain mechanism in place so that when I fulfill certain objectives of my task, I'm able to go to a block state. Okay, or I will go to a ready state. Okay, so you must put in certain mechanism inside your code so that after I do what I'm supposed to do, I'm able to give up the CPU to allow other tasks to run. Okay, so that is the whole idea here. So certain aspect of your coding will change. Okay, certain aspect of your coding will change so that I'm still going to run indefinitely, but at the same time allow other tasks to run. So we will see that along the way. Okay, so of course, when you create a task, you're only putting it to the ready state. Okay? For me to go from ready state to run state, the scheduler is the only one who can do that for me. So I also need to call the scheduler in order for my task to run. In this code, your task 1 still cannot run. Okay, in this code, your task 1 still cannot run because you only created it. Always remember, when you create it, you are putting it in a ready state. But to go from ready to run, only your scheduler can do it. And your scheduler is not yet called over here. Okay, so I must actually explicitly start my scheduler. Only when I start my scheduler, then the tasks that are currently in the ready state can go to my run state. Without a scheduler, nothing will happen. It will still be a normal single-threaded application like how you are doing currently. Okay, only when the scheduler comes in, then it becomes a multi-threaded program. Okay, so you have to remember, I must create the task. Okay, I must also call the start scheduler in order for the multitasking to actually start happening. Okay, if not, it is still in a single-threaded environment. Okay, so your free RTOs is a priority-driven scheduler. That means what? That means automatically the task with the highest priority will be chosen to run. Okay, so no matter how many tasks that I have, the task that is currently the highest priority and is ready. Okay, the task must also be ready. Then I will select that particular task to go to run state. Okay, so that is how the free RTOs will make a decision. If I have a lot of tasks at the same priority and they are all ready, then it will do its own internal time slicing. Okay, if I have a few tasks that are all having the same priority and all are ready at the same time, then I will do time slicing internally to give equal share to everybody. Okay, so again, we will be covering more details along the way. Okay, so let's look a bit into the context of the ATmega microcontroller. So this is again very specific to the ATmega microcontroller. If I deal with the ARM microcontroller, this register will be different, because if I deal with ARM, then I have R0 to R14. Okay, then I have different set of registers here. So this is again specific to the ATmega. Again, no need to worry about too much details because we are not doing assembly language programming, but you still need to understand the concept of what is happening at the low level. So within the context of execution, we know that whenever I'm executing, actually I'm executing assembly language code. Alright? Even though I write in C, I write in OS, doesn't matter. When I compile, it all goes down to assembly language code, which is translated by your processor. Okay, so when I'm dealing with assembly language code, which means what? That means I'm dealing with registers, I'm dealing with the stack, I'm dealing with a program counter. Okay, all these low-level stuff at the microprocessor level. Now, if I look at it from a task perspective, so again, your mindset is what? Each task is like a mini program running by itself, correct? Each task is a mini program running by itself. That means within the task itself, I have a copy of all my registers, plus my program counter, plus all the other registers and memory. And what do I need to do? I must make sure I'm keeping track of where I am within the task A stack. Okay, what is this task A stack? This task A stack is the stack that is created for me when I create or start the task. Okay, so if I look back here, okay, so this is your stack that. How many bytes? Correct, how many bytes I set aside for my stack. Okay, so this allows me to save the status of my task, okay, before I actually start executing and doing a context switch. So just now you saw that I have this idea of context switching, correct? Okay, that means if I'm currently in process 1 and process 0, if I'm currently running and I want to do a switch over, okay, and process 0 wants to do a run. Okay, so I need to do a context switching. And this context switching means what? Current process, everything must be saved. The new process, everything must be restored. Correct? So when I do a save and restore, where does it go to? It goes onto the stack of the current process or the current task. So every task has its own stack space here. Okay? So when I am currently running task A, and then I say that now task B wants to take over. Correct? What must I do? I must be able to take all the information of task A and save it onto the task A stack. Okay? Information means what? That means all the register values, exactly which line of code I was executing, all my data, all my variables, everything I must save on the task A stack. Okay? And then I must keep a copy of the task A stack pointer within the OS itself. And then what must I do? I must load the task B, correct? The new task. So what will I do? After I load everything onto the task A stack, okay, I must do a copy of the task B data stack back onto the current microcontroller stack space. Okay, so what am I doing here? Okay, so again, look here. Currently, I'm trying to do a context switch from task A to task B. Okay, so currently what is executing? My task A. So my program counter is also pointing to my code inside task A, correct? Okay, program counter is what? Is the program count, is the register that keeps track of which instruction I'm supposed to execute. Correct? So everything is pointing to task A, task A, task A. Okay, and all my register of a microcontroller is also holding the data related to task A. Correct? Now I'm saying that I want to make a switch. Okay, so what do? I need to make sure that the program counter value is also pushed onto my stack. Okay, once my program counter value is pushed onto my stack, that means I know that, okay, this is where I left off, correct? Okay, so I'm going to now suspend task A. So since I'm going to suspend task A, the program counter value of task A is now pushed onto the stack. So I know that this is where I left off in task A. If later when I get a chance to come back, I know where to carry on. Because I will retrieve this information from the stack of task A. Okay, so this is how I know exactly where I left off and how to resume. Okay, so the program counter of task A is saved onto the stack of task A. Okay, and once that is done, all the context of task A is also saved onto the stack. So when I say the context of task A means because now task A is executing. So all the register information, all the status registers, everything I must save onto the stack of task A. Okay, and then I keep a copy of the stack pointer, and what do? I load all the data from task B stack. So task B stack also has its own copy of all the register and the program counter and so on. So if I look at it from the program perspective, okay, task A was running. At some point of time, okay, your program counter was pointing here, and then task B says it's going to take over. Correct? So all this data, this address here of where to execute plus all the data related to the processing, all this information must be dumped onto the task A stack. Correct? And then now task B want to take over. So task B may also have been preempted before, correct? Or it could be running from the first time. We do not know. But all we know is task B also has a copy of all the register, plus it also has its own program counter telling where to start execution for task B. Okay, so all this information, all the register information of task B plus where to start executing task B is stored within the stack space of task B. So you have to remember that the stack space of each task contains all the information related to the task. Where I left off, what are all the register values, what is the data, what was it processing. All this information is stored within the stack space of a particular task. So now when task B is going to resume, all I need to do is the OS needs to go to task B stack space, take all this information and put it back to the microcontroller. So it knows exactly where to carry on, how to carry on, what was the data it was processing, and so on. Okay, so that allows me to now move and restore the context of task B, okay, from task B stack space, okay, and resume operation. Okay, so basically what it will do is it will make a switch, and now the PC program counter will point to now task B code, and task B will start executing. Okay, so this is the whole concept of context switch between one task and another task. Okay, so again, if you have studied microprocessor, all this register would have been relatable. If not, don't worry too much. Okay, we will recap this again before we go to the next chapter. But the whole idea is I have task A and task B, and while task A is running, any point of time, it may be preempted, and task B may be running. Okay, again, task B may be preempted, and task C may run. And after task C may be preempted, and task A may run. So this continuous switching between multiple tasks is happening many times a second. Okay, many times a second. So what is important is the OS must be able to keep track. Task A was running up to a particular point, and then it was give up here, alright? So when I eventually get a chance to resume, I must know exactly where to resume. Correct? And how do I know where to resume? All this information for each task is saved onto the stack of the task. Okay? So when I switch out and I switch back, I just take all the information from the stack, load it back to the microcontroller, and start executing again. Okay? So I know exactly where I left off, and I can carry on without losing any information. Okay, so that is the whole idea behind context switch. Okay, so the example code and all, don't worry, when we are doing your lab, okay, you will get an idea of how to compile RTOs inside and how to write OS-based code. Okay, so that's the end. Okay, so we will end here today. Okay, next week, then you start the new chapter. So again, remember this Wednesday, you're supposed to do the demo. And your submission is into your submission folder in IVLE is next Wednesday only. Okay, it's only next Wednesday. Okay, so wish you all a happy new year. Enjoy your long weekend holiday break. Okay, and I'll see you all next week.